Okay, what we're going to do today is we're going to do the simplex method. I am not going to prove why the simplex method is as efficient as it is. Why this is a first course in the subject, there's only so much time we have. What is the best use of the time? My feeling is it is not the best use of the time to show how well it works. But if people are looking for projects, one great project would be to read about why the simplex method runs as efficiently as it does and then present that to the class. So if you're looking for something to do, that is a great project. There are several more projects that are coming along our ways. I have been talking with several people who will be hopefully coming in the near future to do presentations. So that if you want to work on something that has real impact, that will be possible. If you want to continue this as a winter study, I have talked to the Center for Learning in Action, and I will be running a section on stuff like this. There's also kinetic, which is another option. Okay, it is time for the simplex method. Before we do the simplex method, we're going to make some assumptions. So we have a canonical linear programming problem. And this has three pieces. Ax equals b, x is greater than or equal to 0, and we want to minimize C transpose x, where x is going to range over all feasible solutions. So here are the assumptions. We're going to assume the following. 1. A is m by n, so this is the rows, this is the columns. With m, what do you think? Do you think we want more rows or more columns? What do you think? Yes?
More columns.
More columns. Excellent. Where m is less than n. 2, let me just make sure I'm going to get them in the same order. Okay. The rows of A are linearly independent. And then 3, B is not a linear combination of fewer than m rows. All right, so these are the three assumptions we're going to make. Let's investigate how severe they are. The first one is we are assuming we have more columns than rows. What would happen if we actually had more rows than columns? The system is overdetermined. Okay, what if we had exactly the same number of rows and columns? There's at most one solution. Well, unless we have like a null space, but in general, we will essentially have, unless something really degenerate happens, the system will either be overdetermined or there'll be at most one solution. I want you to maximize, I want you to find the optimal choice given that you have to do this. Okay? So, how do you find your optimal choice given you have to do a specific thing? What do you do? No. Do that thing. Is this hard? I'm sorry? No! Try again. If you can only do one thing, is it, okay, I'll rephrase it. Is your choice difficult? And I don't mean are you internally, you're feeling anguish, uncertainty. If you only have one thing to do, is it clear what you need to do? Yes. You may not want to do it, you may not like the result, but there is only one thing you can do. If the system is overdetermined and there's at most one solution, I really am not going to expend too much time trying to develop a theory of how to find the optimal choice when confronted with one option. When you're confronted with one option, the optimal choice is clear. Okay? The first elected office I ever had was for a social chair in graduate school. There were 3 candidates running for 3 positions. So I put up signs, why vote for the lesser of 2 evils? Vote for both, because I was running with a friend of mine. I was sponsored by Cinch, candidates in non-contested hollow elections. Not surprisingly, we won. We gave the people no choice. Now, it was more interesting the next year when there was a competition. But when there's one choice, it's clear. So, otherwise, overdetermined. Or typically, one choice. All right, what about the second one? The rows of A are linearly independent. Is that a severe assumption to make? Okay, so what would happen? How could rows of A not be linearly independent? Give me one way the rows might not be linearly independent. Simplest way for the rows of A not to be linearly independent. Yes? Two rows are the same. So if the two rows are the same, you have two options. Either the corresponding B's are the same, or the corresponding B's are different. If the corresponding B's are different, is there going to be any feasible solution? No. So if two rows are the same, either one of the rows is completely redundant, and you can just delete it, or you're screwed. Either case, it's easy to figure out where you are. What if you have a couple of rows that are linear combinations of each other? You have the same general principle. Either you have a solution, either the B's lie in the correct space, or the system is inconsistent. So it's redundant or inconsistent or redundant. Okay? One of those three happens. So without loss of generality, can we just assume that the rows are linearly independent? Yes. We have fewer rows than columns, so we are fine. Remember, the rank of a matrix, the number of independent rows or columns, is always at most the minimum of the number of rows and number of columns. So if we have a 5 rows, 12 columns, the dimension of the row space is at most 5, the dimension of the column space is at most 5. So we will assume that if there are any repeated rows, we've removed them. If they were inconsistent, problem is not solvable, no feasible solutions exist. The last one, B, is not a linear combination of fewer than m rows. This one is a more interesting condition. And this is needed for some stability issues. Stability, bless you, and technicalities. So how bad is it to assume B is not a linear combination of fewer than m rows? Well, if B is the linear combination of fewer than m rows, what is this going to mean? It's going to mean that B is degenerate in some sense. So let's think about what's going on. This is a good way to review some linear algebra. We have m rows, and we have n columns. And here's A1, here's A2, here's AN. Here's X equals B. What's the maximum dimension of the column space? I'm sorry? I'm sorry? I can't hear you. You've got to speak clearly. We have n columns, but we know it's not n. What's the maximum dimension of the column space? Yes. M. Because the column space, this is one of the theorems from linear algebra, is at most the minimum of the number of rows and the number of columns. So since we have m rows and m is less than n, the column space is at most m-dimensional. Where does B live? How many entries does B have? M. Okay? X has n entries, and then AX equals B. B has m components. So the question is, what is the probability I choose a vector B at random, and it lives in a linear combination of fewer than m columns? Okay, let's take the simplest. What's the simplest possible B to take? all zeros, okay? What's the probability I chose the vector that's all zeros? 0. 0 probability. Right? No columns. B has to be the 0 vector. This happens with probability 0. What's the next possibility? One column. How many ways can I choose one column? How many ways can I choose one column of the n columns? N. Write it, or say it like a combinatorialist. N choose 1. So one column gives n choose 1 lines. What is the m-dimensional volume of a line? 0 times n minus 1 is still probability 0. More generally, say we're a combination of k columns. How many ways can we choose k columns from n? And choose k. And this gives us hyperplanes. And we're assuming that k is less than m. What is the volume of these k-dimensional hyperplanes? 0. If you take a plane in 3-dimensional space, what is the probability I hit a plane in 3-dimensional space? 0. Right? So this would also be probability 0. Do I have finite or infinitely many things? Finite. So a finite sum of 0 is 0. So the probability, if I choose B at random, the probability that B happens to be in a lower dimensional space is essentially 0. Because I'm assuming my column space is m-dimensional, the probability I land in a lower dimensional space, it's not even worth considering. Now, of course, then what happens if you happen to have a B that lands in something like this? You can tweak the coefficients of B ever so slightly. And if you just tweak the coefficients just a little bit, then you will be, with probability 1, a linear combination of m columns. Okay? Okay? Then you get questions about, well, how much will my answer change if I change the coordinates of B just a little bit? Do you think the answer should change a lot or a little as you vary B just a teeny, teeny bit? What do you think? Hopefully there's some kind of continuity that goes on, and if we move B by just a small amount, hopefully that doesn't change things by that much. So we're not going to get into that, but I want you to be aware of some of the technical issues. Okay, so again, is this a severe assumption? No. In the real world, if you have any real data, the odds that you would land in a low dimensional space is fairly unlikely. If I choose a 3 by 3 matrix at random, what's the probability that its determinant is 0? So what's the probability if I write down a matrix at random, its determinant is going to be 0? 0. You've got this massive polynomial equation that has to be satisfied. The odds that you can write down a matrix at random, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the probability that this matrix has determinant 0? It's either 0 or 1, because this is no longer a random matrix. This is a highly structured matrix. How many of you have seen this matrix before? Do you agree that if you want to write down a generic 3 by 3 matrix, this looks like a really good choice? Turns out it has determinant 0. If you look at 1, 2, 3, 4, all the way up to 16, that has determinant 0. If you go 1, 2, 3, 4, 5, all the way down to 25, that has determinant 0. So if you take all the matrices going from 1 to n squared, that always has determinant 0. So it's a nice exercise if you want. This is a good way to practice your linear algebra. Prove all of those matrices have determinant 0. The main reason I'm saying this is if any of you ever become a linear algebra professor and you need to write down a generic 3 by 3 matrix, be very, very careful not to write this down because it has determinant 0. Are you surprised that this has determinant 0? But after the fact, it's not so surprising because this is a very special matrix. What about the following matrix? 1 pi e square root of 2, 1701 over 3, square root of 666, 4 to the 1/3, 8, and e to the e to the e to the 2. Okay? I now take this matrix. If this had determinant 0, my God, I got lucky. Okay? This has so much randomness in here. The kind of algebraic relationships between these numbers would be phenomenal. Okay?
Check.
Can we check? You can check. You can check this. Actually, it's not that bad to show. I think these two numbers are large enough that their product might dwarf everything when you look at all the other possibilities. But if not, let's cover myself a little bit more. So if we do this, I'm definitely safe, because now when you look at all the different, you'll have 3 factorial different products. You look at pluses and minuses of them. With this now, it's so large that I'm okay. Okay. So you do want to be careful. There are situations where it may not be completely generic. And if it's not completely generic, you have to be careful. But again, the assumption that B is not a linear combination of fewer than m rows, that is a very reasonable assumption. Okay. Any questions about the assumptions? Do we agree that the first two are very reasonable? I'm going to add one more condition. And I'm going to add a condition on B. I'm also going to assume that B is greater than or equal to 0. Am I allowed to just assume B is greater than or equal to 0? I'm trying to solve AX equals B, and by the way, you can only look at output B's that are greater than or equal to 0. Is that a severe restriction? Yes.
Well, if you're talking about this is an implied problem.
Yes.
So B is some sensor output.
Uh-huh. Well, but maybe some of your things are not profits. Maybe some of the things are losses.
Well, the other way around.
Maybe some are profits and some are losses. Or maybe you have some inventory and maybe you're buying some of stock A and selling some of stock B. Yes?
You can just multiply the corresponding row.
Excellent. Without loss of generality, we may take B greater than or equal to 0. If a BI is less than 0, multiply row I by -1. So there's really no danger in assuming that all of the entries of B are greater than or equal to 0, because I can always change my matrix A. Did we ever make an assumption that the matrix A has positive entries or non-negative entries? Did we ever assume that? No. You've got to be careful. There's only so many things you can fix and normalize at the same time. I can fix B at the cost of A. Can I assume all the entries of A are non-negative? No. That I can't do. Okay? But I can assume all the entries of B are non-negative. That's no problem. That just changes the things in A. Okay, any questions about all of our assumptions? So the whole point now is we have a canonical linear programming problem. AX equals B, B and X are greater than or equal to 0, and we're going to look at the minimum of C transpose X. And our goal is to try to find a way to solve this efficiently. And this is where the simplex method comes in. So, simplex method. There's 2 steps to the simplex method. They're historically called phases. So phase 1, find a basic feasible solution or prove none exist. Okay, that's phase 1. Phase 2, given a basic feasible solution, find a basic optimal solution, or you get a sequence of feasible solutions with cost heading to minus infinity. And if the cost is going to minus infinity, there's no optimal solution. Because again, we're trying to minimize. So whenever I say cost, this is the C transpose x. We often refer to C transpose x as the cost. All right? So what does phase one do? Phase one either tells us, hey, here's a basic feasible solution, or it tells us no basic feasible solutions exist. All right? Phase two, given a basic feasible solution, it will then find a basic optimal solution, which is what we want, or it will tell you that it doesn't exist. This is more than you could hope to ask for. How is it telling you it doesn't exist? Oh, by the way, here's a sequence of choices where you can make the cost as small as you want, as negative as you want. That's a good thing, right? This is not just an existence argument. This is a constructive argument of why there's no optimal solution. It's giving you, here's a list of candidates. Okay, so this is the simplex method. So if you were looking at these, phase one, phase two, step one, step two, which should you prove first? Phase one. Why should you prove phase one first? Because it's the first. Okay, very good. Okay, excellent. You all belong in a 300 level class. So let's say method of proof. So step one, assume can do phase two, prove can do phase one. And then step two, assume can do phase one, prove can do phase two. Okay. So that's the simplex method. This is how we're going to prove it. Any questions? Any issues or concerns? Yes? Yeah, you can't even say it.
Yeah. In step one, why do you need to assume you can do phase two?
Oh, because that's how I can prove step one. Yes?
Is that kind of circular?
No, it's actually not circular. It's linear. And here. It's linear, okay? Linear.
Did you bring that just for today?
I actually brought this for all my classes, and for those of you at home. I really need this only in 331, the little questions. But I figured as long as I bring it into the little questions, I should really maximize my chance of getting into trouble with the administration and use it in all of my classes today. I'll leave this, no, I'll leave it. No, I don't want to risk leaving it that close to you. Okay, so there are some real concerns about this plan of attack. Why is it circular? Yes?
Well, phase two isn't true when you used it to prove phase one, and then you assume phase one is true when you prove phase two.
Yeah.
They can both be wrong, and then they're both right.
So there's some issues with this. Yes?
Well, really, you're just showing that either they're both wrong or they're both right, right?
No, because at some point I have to get on the merry-go-round. I'm not just transported to the merry-go-round. At one point, I've got to prove something. If I assume this, I can prove this. If I assume this, I can prove this. If at some point, I've got to prove something. So it's really subtle as to why this is not ridiculous.
Is it what we did the other class?
Nope. So this is one of my favorite proofs, I think, in all of mathematics. Because at first it looks like you're doing something that is completely ridiculous, completely unallowed. I want to really pass what we're doing. Come on. Okay, so phase 1, find a basic feasible solution or prove none exists. Phase 2, given a basic feasible solution, if you find a basic optimal or you prove that one doesn't exist by giving a sequence where the cost goes to minus infinity. When you're trying to find a basic feasible solution, what do you care about? So when I care about this, what part of my canonical linear programming problem do I care about? I care about A, x equals b. What else? Anything else? At this point, I don't care about anything else. Over here, given a basic feasible solution, find a basic optimal solution. What do I care about?
The cost vector.
So the cost comes in. What else do I care about? Is that the only thing I only care about the cost? Do I care about anything else? I only care about the cost in this? There should be something else I care about. Yes?
You still care about ax equals b and x greater than or equal to 0 because you're finding a new solution.
I'm close to agreeing with you, but you're being very discriminatory. It's really subtle, yes.
Is it just that you care about x being good and equal to 0?
You're still being discriminatory.
And b.
Still being discriminatory.
We care about everything.
All right, you're at least not being discriminatory.
If x hat satisfies that, then it minimizes c transpose x hat.
So you are saying that I'm applying this to the same problem. I care about something maybe b x twiddle equals maybe b twiddle, x twiddle greater than or equal to 0, and maybe c twiddle transpose x twiddle. And I want to minimize that. I do not have to apply this to the same linear programming problem. That's the beauty of this proof. Imagine you have a related problem. This has to be related to this somehow, or this is not going to work. So somehow b should be related to a, x twiddle should be related to x, b twiddle should be related to b. Imagine I have a new problem where I can find a basic feasible solution. So imagine you own US Air. There is a trivial solution, which I do insist US Air is close to using, as somebody who's been flying US Air a lot. What is the trivial solution for US Air? I'm sorry?
Don't fly.
Don't fly. And from several past experiences, they seem to be very close to that at times. Can you show that you satisfy all of your constraints? That you don't have the plane, one plane being used on two different routes at the same time? That after a plane lands, there's at least a certain amount of time before the plane is used again? That the plane is not going further than its fuel capacity? Every constraint is satisfied. So is it easy to find a basic feasible solution to the US Airways problem?
What about like not breaking even on your fixed cost?
That's different. That's desirable. But US Airways is not necessarily forced to break even. Now again, they will not stay in business if they can't at least break even.
That is not a constraint.
But that's not a physical constraint on choosing valid flights. That is a constraint to stay in business unless they can get big government bailouts. But that is not the view of this class. That is a view of an economics class that you can go to. All right, US Airways, there is a trivial, basic, feasible solution. This should be laughable. Let's take a harder problem. Let's take Major League Baseball. Okay, you have 162 teams, two leagues, several divisions. You want to come up with a valid schedule. There are a lot of highly desirable things you would like in your schedule. What is something you would like in the schedule? And if you want, you may assume the Red Sox and Yankees are good teams for the sake of discussion. Yes?
We want the Red Sox and Yankees playing each other in the last series of the year.
Good. Why do you want them playing in the last series of the year?
Hopefully there's a playoff spot on the line.
Hopefully there's a playoff spot on the line. In fact, they try to have division games at the very end of the season. So if you think about who is playing whom, Sox ended with the Yankees. Detroit's playing Kansas City. Lots of stuff like that. What days do you want the Red Sox and Yankees playing for the most part? Yes?
You probably want more important games played on like holiday weekends or days that a lot of off work can go.
Right. Weekends, Red Sox, Yankees, typically that would be a Saturday game. And, I would normally say Kansas City, oh, yeah, let's put them in the middle of the week. That's not as, this year, Kansas City is doing very well. So you would have some constraints like this. You have other constraints about how often you play each team. Is it easy to come up with a valid schedule? That's a little bit more work. What you could probably do is maybe have things paired. Red Sox play Yankees, Blue Jays play Orioles, and then maybe Red Sox play Blue Jays, Orioles play, no, screw, we've got the Tampa Bay Rays, we've got to put them in. Without too much trouble, you can probably come up with a schedule. It may involve teams flying constantly across the country, high cost. But you can probably come up with a feasible schedule for baseball. Right? It would have a lot of highly undesirable things, but it might be solving a related problem. And then you try to go. So the idea, the genius behind the proof, is we start off with a related problem where it is clear what the basic feasible solution is. And then we solve that problem, and we find an optimal solution to that problem. And the optimal solution to that problem is going to be what? What do you think it's going to be? We have a related problem. Let's assume that related problem has an optimal solution. What would we love that optimal solution to be?
Basic.
Basic for which problem? So we have an optimal solution for the new problem. We would love it to be a basic feasible solution to the old problem. That's why this is not a circular argument. So the way it's going to work is we take a related problem where it's trivial to find a basic solution. If it's trivial to find a basic feasible solution, do we have to worry about how to do phase one? No, phase one is a procedure that in general, this will give you a basic feasible solution. There are times when I don't need it. So let's try to give you an example. Your grade depends on calculating the following. I want the roots to x squared minus 1701x plus 24601. Can you find the roots of this? If you're not saying yes, there's issues. How would we find the roots? Quadratic formula. Is it enjoyable? All right. What if I give you x squared minus 3x plus 2 equals 0? What are the solutions? Okay, x minus 1, x minus 2. How did you do the quadratic formula in your head so quickly? How did you do the quadratic formula so quickly? Try again. Answer me. How did you do the quadratic formula so quickly? I kind of like this, actually. Did you do the quadratic formula in your head? No. What did you do? You factored, you just looked at it, and you felt it, right? You felt the roots and the force. You could just look at it, you could just see it. Was there a need to use the quadratic formula? No. Is it nice to know that you have the quadratic formula as a crutch? Yes. But for a lot of problems, you can just look and see the solution. This is like 20 levels deeper, but it's the same principle, right? There are lots of times when you can just look at the problem and see the answer. This is called the method of divine inspiration. It is one of the greatest methods in math. If you just happen to know the answer and write it down and check and show it works, you're done. What's the problem with the method of divine inspiration?
It's almost impossible. The problem gets harder.
It gets harder as the problem, well, for some, yes. I mean, unless you're truly divinely inspired, it can get very hard to just see the answer. Okay? For Fibonacci numbers, for Benet's formula, I can just write down the nth Fibonacci number is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. I just saw that. And then you can check and see that it's right. All right. Let's now show how to use phase 2 to do phase 1. Okay. Showing phase 2 gives us phase 1. So we start with ax equals b, x and b are greater than or equal to 0. So we're going to consider the new problem. I'm going to expand my matrix A by adding an m by m identity matrix. So this is a new big fat matrix. Okay? And I'm going to add some new entries. And I'm still going to assume that x and z are greater than or equal to 0. And I want to minimize. I have complete freedom in terms of what I want to minimize. I can choose anything. Why can I choose anything? Because at this point, do we care about what we're trying to minimize in the original problem? We're just trying to show that there is a solution. So again, USA probably can do better than flying no planes. But right now, we're just trying to find that. We are going to assume right now that we were not clever enough to see that US Airways could just fly no planes, although US Airways seems to have discovered that. We'll consider maybe that we have a more difficult problem where it's not clear what the solution is. We can choose whatever we want to minimize. Let's minimize z1 plus zm. So this is going to be the vector 1 transpose with z. We want to minimize that. Okay, yes?
So just for clarity, I is m by n.
I is m by m.
And when you write a, I, you're writing, it's a
yes, right. And so in fact, I was about to just write the ith row is going to be ai1 x1 plus ain xn plus zi equals bi.
And so the AI in parentheses, some other people would write that as A00I.
No, you would not write it as A00I. I'm appending this matrix I to it.
Okay.
So for instance, if A started off as 1, 2, 3, 4, 5, 6, this would be my new matrix. This would be A, this would be I. So this would be the appendation, if that is a word, of A. All right, this is a new problem. How many people feel divinely inspired? I need at least one person to feel it. Come on. Who's feeling divinely inspired? Somebody give me a choice of z's and x's that solve this equation. I'm sorry? Excellent. Remember to email me. Right? Solution. X is 0. Z equals b. Fortunately, somebody was divinely inspired, and we only needed that once. This is why we chose b to be greater than or equal to 0. Now you can see why I wanted that simplification, because now I can quickly write down a solution. Let's check. Is it feasible? Yeah. X and z are greater than or equal to 0 because b is greater than or equal to 0. It satisfies this new matrix, gives me b. So we have a feasible solution. Is it basic feasible? Yes. Because the corresponding entries of my matrix corresponding to z are going to be just vectors with exactly one entry that's non-zero. So we get a basic feasible solution. This is why it's so great that we've put in the identity matrix. Any subset of its columns are linearly independent. So we now have a basic feasible solution to this problem. We now apply phase 2. What does phase 2 do? It says, well, look, given a basic feasible solution, got it. It finds a basic optimal solution, or tells us that no basic optimal solution exists by giving us a sequence where the cost goes to minus infinity. All right, let's look over here. Is it possible that the cost could go to minus infinity? Could the cost get arbitrarily negative? Or is there a minimum as to what the cost could be? What's the minimum cost? 0. The entries, the z's, are non-negative. What's the lowest possible cost? All the z's are 0. So when you look at the set of all feasible solutions, the cost can never be negative. All right, so I'll try to keep phase 2 up. Cost cannot go to minus infinity as it's at least 0. Great. So phase 2 tells us that given a basic feasible solution, we either have an optimal solution or we have a sequence of solutions whose cost goes to minus infinity. Since the cost doesn't go to minus infinity, there must be an optimal solution. So, bless you, must have optimal solution. Let's call it XOP, ZOP in hopefully obvious notation. Yes?
Can you explain again why we know the cost doesn't go to negative infinity?
Sure.
Do anything about the cost function?
Well, we got to choose the cost function. Remember, it's not the cost function of the original problem. We can choose any cost function we want. The cost function I chose was z1 plus z2 plus dot 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 plus zm. And since the z's are non-negative, the smallest cost we can have is when all the z's are 0. Yes?
Does the simplex method stipulate that it must be a basic optimal or just optimal?
We already know that if there's a optimal, there's a basic optimal. So it doesn't really matter. And when I said that we get a basic feasible, I could have said we just get a feasible. It doesn't really matter. If we have a feasible, we have a basic feasible. So we know the cost can't go to minus infinity. So the only thing that's left is we have an optimal cost. What are the possibilities for the optimal cost? So what are the possibilities? Yes? I'm sorry? It will be less than or equal to b, good, because we know less than or equal to the sum of the entries of b. I want something a little bit different, a little bit cruder. We know the optimal cost can't be negative. What are the other two possibilities? 0 or positive. So case 1, optimal cost equals 0. Thus, what must z optimal be? If the optimal cost is 0, what must z optimal be? The only way we can get a 0 cost is if all the entries of z are 0. Therefore, what do we know about XOP? This is the punchline. What do we know about XOP? So we have an optimal solution to our new problem. It's an optimal solution to this system. We now know all the entries of z are 0. Well, if all the entries of z are 0, what do we know about x? It's basic feasible for what problem? It's basic feasible for the original problem. So we get XOP is basic feasible for the original. That's exactly what we wanted. So in the case when the cost is 0, we now have a basic feasible solution to the original problem. What's the other case? So case 2, optimal cost is greater than 0. If the optimal cost is greater than 0, what do you know about the z's? Some of them have to be greater than 0. And I claim this means, so some zi is greater than 0, no basic feasible to original. Else, the cost would be 0. So imagine we had a feasible solution to the original problem. If we have a feasible solution to ax equals b, what could we take all the z's to be? 0. And what would the cost be? 0. So if there is a basic feasible solution to the original problem, what must be the optimal cost to this new problem? It must be 0. Because the optimal cost is greater than 0, could there be a basic feasible to the original problem? No, we would have had a better cost. So we have now shown that if we can do phase 2, we can find a basic feasible solution. Okay? I deliberately wanted to go slow on this because this is one of the strangest proofs I've ever seen. It seems like you are doing a circular argument. The first time I read this proof when I was an undergraduate, I was quite confused as to what was going on. And it took a while before I realized we're not doing phase 2 and phase 1 to the same system. That's the trick. And this is a great mathematical idea, is we have this ability to play things off of each other. Okay? So it's not because somebody has a loud voice, it's not because somebody has serious firepower, it's because we can choose what systems to apply to. I am applying phase 2 to a system where it is blatantly obvious, at least if you're divinely inspired, what a basic feasible solution is. This was constructed deliberately to make finding a basic feasible solution easy. Is it easy to look at this and find a basic optimal solution? No. But we are assuming that we have a method that once you give it as an input a basic feasible solution, it will churn away and it will come up with the basic optimal or tell you that no basic optimal exists. Okay? That's why this method works. Okay, any questions about this? All right, so this is a good place to stop. There will be a review session tomorrow at 8 o'clock. And then have